So, good evening, all of you. A very warm welcome to all of you from the Indian Space Society's family to this webinar. Now, let me first introduce the guest of honor, Mr. Sem. He is right now the managing director at B Space GmbH, where the founding members have the expertise in planning, developing, operating small satellite missions, engineering projects, space training program, even, and lot more. To note, he is also a professor and the scientific coordinator of the TU Berlin Master Space Engineering Program. He has several research publications to his name and has made notable contributions in the field of space engineering. Now, I would personally then like to thank him for accepting our invitation on such short notice and being so gracious about the whole event, I must say. Now, without delaying any further, let's hear from the man himself. And sir, the session is all yours.
Okay, wonderful. Thank you very much, Samar Patel, for this nice introduction. And it's great. It's an honor for me to be here and to give a speech for the Indian Space Society. And I'm sure that there are many young talents in this session right now, eager to hear more about space engineering, some satellite technologies, and how to get involved in that field further. So I'm just going to share my screen real quickly.
I'll give you the access to it. Yeah, please go.
Thank you very much. And then I'm going to dig in right into the topic. So the topic today is, you can see my screen, right? Everything's,
yes, of course.
Everything's good. Okay. So it's about academic small satellite mission design. And who am I addressing today? So mostly I'm addressing students and researchers who want to start a satellite mission, a small satellite mission, or who are already doing the first steps in that direction. So it's up to you. As a student, you can initiate a project like that and make small steps towards a real mission, and you can set up you can create a vision for your department at the university, and then go into such a project. Basically, I have several backgrounds. Just briefly about myself. So as Samar said, I'm managing director of B-Space, and we're strongly focused on space education. So one of the projects that we do is we run an international master's program, the Master of Space Engineering at the Technical University of Berlin. And I was also a researcher at the Technical University of Berlin, so the deputy of the chair of the space technology, which has several projects. So I've been working on satellite missions. I've been teaching several subjects. And my passion was always towards doing hands-on education with students, like students who are eager to learn, who want to try new things, who have the courage to try new approaches. And so I took part in several competitions with the students building rovers or other systems. So today I want to talk about, I'm just going to briefly introduce for a minute or two what we do at TU Berlin, so that you have an idea like what my background is, where I come from, where this experience comes from. And the second is I'm going to talk about key factors for starting a university satellite project. So this is kind of like a brief guideline, a manual for you to say, you know what, I could talk to my faculty and to some students, and maybe start a movement in that direction. So I'm going to talk about preparations, design to operation, going through the different phases, and showing what is necessary in each phase. And then also some academic aspects. It's really difficult, as you can imagine, really challenging to set up a satellite project from scratch. I mean, there's so many things that make it more difficult than if you're in the industry and want to start a satellite project. So I'm going to give one short example of BISA-3, which is a fully student-built satellite at TU Berlin. And then, of course, you can ask any question about anything you want after that. So it's going to take roughly half an hour until we have time for questions. So this is the chair of space technology. We're on the rooftop here with the S-band antenna and some other antennas. So the satellites are built at TU Berlin. They're operated from TU Berlin. Around about, I don't know, 60, 70 staff members and students working on different projects here at TU Berlin. So we have, of course, a strong focus on education and also on research, and thus we provide lots of practical experience where students can build rovers, so for planetary exploration, although this happens on ground, of course, autonomous vehicles that are able to detect their environment to potentially help astronauts. And then they can build satellites and satellite equipment, small satellites especially, and they can also build rockets at the department. So when you look at the landscape in Europe, so you see Germany here, and the cities that actually build satellites in Germany, and you can see that Berlin with 21 and counting towards 30 right now, satellites, small satellites in orbit as a university. So those are only the university satellites. Berlin is kind of like the small satellite hub of Europe. So it's where most small satellites are developed in Europe, and not only by the university, but also by other companies that are located in Berlin. And so the chair of space technology, which is in the Department of Aeronautics and Astronautics, it's a dedicated chair to develop satellite technologies, focuses on miniaturization of space systems. So we build small satellites, small rovers, small sounding rockets, but also ground stations. We have distributed research in distributed space systems. So we have constellations of small satellites in orbit. And one big area is the component miniaturization. So in different sectors like attitude control, how can you build smaller, more efficient components that allow attitude control? You can see the fleet of the TU Berlin satellites, and is actually going on further with new projects in the pipeline. And they have several purposes, the satellites here. Some of them are for technology demonstration. So when we started early in the 2000s, it was more about with the first CubeSats, it was more about showing that such a satellite, such a tiny satellite that has 10 centimeters of size and as a cube, can survive in an environment like space. And the nominal lifetime is 1 year. However, all of the CubeSats that you see here are still operational. It is true that with commercial off-the-shelf equipment, if you do proper testing, if you do proper material selection, and if you implement failure tolerance in an appropriate way, then you can create really long-lasting small satellite missions. And but other missions also, like Tubin, for example, is focuses on Earth observation. We have an infrared payload that can detect forest fires. We do experiments in communications where we try to have a fleet of 4 satellites in the 10-kilogram range in orbit, where we try to improve the communication between satellites, so to improve the network communication in space, and so on. So there are several different purposes of the satellites. I'm just going to talk more about CubeSats, because for academic projects, university projects, first thing that comes to mind is a CubeSat, probably a 1 or 2 or 3 unit CubeSat. The first one was launched in 2009 from India, actually, and verified all the different equipment, especially miniaturized reaction wheels that were built in collaboration with the industry. So those are really tiny wheels, like tiny motors with masses that can rotate the satellite in every direction. And then 3-axis stabilization was done. And then BSAT-3 is a slightly different satellite. Its main purpose was fully educational. So this was only built by students and sent to space. So the other systems are a bit more sophisticated with respect to failure tolerance and redundancy. So those are some pictures that you can see from the CubeSats alone. So they provide actually quite good quality. So this is from a 20-kilogram satellite, TechnoSat. As you can see, of course, with the size of the instruments, the quality also can be improved drastically. So, and to build satellites, of course, you need some facilities. So we have an integration room where we put together, here you can see the structure of a satellite. and an mission operations center, the ground station on the top of the building. And you can also study space engineering at TU Berlin, and this is a combination of course, hands-on experience where students build systems and learn everything about space systems engineering, but also we have a big space industry in Germany, so do lots of visits and also lots of cultural activities, of course. So now let's get to the core of today's topic. So let's say you have in mind that you want to set up a satellite mission. Then I'll give you some important factors for preparations. So the first thing you want to do is think about a purpose. So of course it's great. I mean, most of you are engineers, I'm assuming, and either students or young scientists, and of course, the purpose of having a satellite, just to have the satellite, I can totally understand you think it's great to build a satellite. But nowadays, especially with more and more satellites coming up and being sent to space, we want to be more responsible and want to give the satellites a clear purpose. So it's best if you write down clear objectives, scientific, they can be technological, and of course, they can be partially educational. That is also not just important to give an idealistic purpose to a mission. It's also important at some point you need money. So you want to send your satellite to space, you want to build it, it's going to cost you money. And you can do certain things at a university without a big budget. So the university can fund the first prototypes and everything. So you can probably even create almost a full CubeSat prototype, probably with university funding. But at some point, you have to do some qualification tests. You have to pay for the launch. You have to build the flight model, which requires you to get like real solar cells, some real equipment. And if you want to acquire funding, then of course it's great if you can show your government or any other funding source that your mission has a clear purpose, a clear vision, that it is sustainable. And it's not just about building a satellite per se. So the second thing is clarify funding and resources. Yes, think about where could you potentially get funding. Like let's say you're a student and you say, yeah, we want to build a satellite. We can probably build a prototype. But about the later steps, like if you want to convince your faculty, you could say, you know what, I don't know, the Indian government could potentially offer a free launch or could potentially provide funding to our university. You can look into national funding sources. That's one thing that you should have a clear picture about. Then what I highly recommend is to include partners and supporters. They can be academic. So you can collaborate with another university, especially in the field of, let's say you're an engineering department, mechanical, electrical, communication, whatever engineering department you are. Normally, small satellite, not many universities have an aerospace department. So many university satellites start in a mechanical engineering department or electrical engineering department, with people having really little knowledge about the space environment and the requirements on a small satellite. And also they want to build the satellite itself and are maybe less interested even in the purpose of it, like the payload part of the satellite. So it can be really helpful to partner up with academia or industry to say, you know what, maybe you from the biology department or any other department have an experiment that you want to conduct in space, and you need a microgravity space environment. So we can build that instrument for you as engineers. We have a clear purpose, and we can also build the satellite. So now we have a partner. Maybe the industry is willing to. You will need test beds at some point. You have to do lots of simulations for. Because the satellite has to survive a launch in a rocket, and that is basically like a bomb carrying your satellite and ejecting it to space, and that is vibrating. It has lots of shocks from state separations. It's a huge mechanical load, and you need to do certain tests, and maybe you can collaborate with academic partners or the industry that have certain test facilities that you can utilize, and maybe they can sponsor you in some way or another. Maybe you can get it for free, even if they if it's okay for you to add them as a sponsor. And of course, the National Space Agency is always useful because they have experience. They can guide you through a project. And then facilities, yes, at some point, production, integration, testing, operations. Where will you set up things? Where will you test everything? How will you perform different tests like vibration or thermal vacuum to test the thermal environment? Radiation testing may be something that you need. Where will you do all of that? That's a question. Think about it in advance, and then how will you do operations? I'm going to go into some more detail in the next steps, though. And then clarify the big constraints. So the big constraints, what I mean with that is who will launch your satellite, for example. So that's a big thing. It costs a couple of 10 or even more than $100,000 to launch a small satellite. If you don't have a free opportunity nowadays, there are also many. That's an interesting thing. Many new launchers are developed worldwide, and to create some traction, and they offer sometimes free launch opportunities because it's their test model of the rocket or something, and they say, you know what, we're going to pick a few small satellites that can launch with us, but we don't guarantee that we can safely take you to space because it's a test launch, basically. So there are interesting new opportunities. There's a high demand for new, smaller launchers that bring small satellites into space. Think about a big constraint like that. Who's your launch provider? Then frequency coordination is something that people really don't have in mind. But you should address this as early as possible. Just imagine you have starting to have thousands of small satellites in space, and every satellite is sending data through a frequency. Just like when you're in your car and you tune into a different radio station. Now you have, maybe in your area you have 50 radio stations. Now just imagine you have 2,000, 3,000 counting up satellites in space that communicate in a certain frequency. You need to coordinate that, and for that you have the International Telecommunication Union, who coordinates the frequencies. And unless you don't have a license for a certain frequency that your satellite may use for communication with your ground station, then you're not able to communicate. It's not allowed. So that's something you need to take care of. And then export control for some countries. If you launch your satellite from another country, then a satellite is not easy to transport, in the sense of, it's high technology, and you need to make sure that you're allowed to carry your satellite to another country. Of course, how you carry it is a different story. So especially CubeSats, you can even take them on a plane. You're so small. But then it's very funny if you go to customs and then they see a satellite that you carry around with you. So you need to write papers. So make a realistic plan. What I mean with that, with respect to complexity, time frame, and budget. So students very often overestimate the capabilities. So they aim for a very high and complex goal very often. So you need some people, some consultants with experience to get you more on the ground level, to say, okay, you know what, it's your first satellite. How are you gonna develop this and that technology? Where do you get it from? Think about an appropriate level of complexity, the time frame, and the budget too. What really helps, and what we do very often, is to conduct a feasibility study. So just suggest, if you're a student, just suggest to your teacher in one of your design courses that you want to conduct a feasibility study for one semester to do mission analysis of a small satellite. You know, like you have different classmates who all look into all the different subsystems, the mission planning, the operations, the budgeting, the management, And then you can create a whole report, you can create a presentation, and then you have a very good idea of what it takes to actually build that mission in the next steps. So it may take you, for the first satellite, it may take you 3-4 years or so. But you want to do proper planning in advance. So this is what we do very often, feasibility studies at the university. And then what you need to think about is the make or buy decision. So for very different systems like your onboard computer, your power control, all the different sensors and actuators that you have, will you buy them or will you make them in-house? So both have their pros and cons. Like if you have a lot of money, you can buy space equipment, of course. You know that it works. It doesn't cost you that much time to integrate them into your satellite. But cost means it's really expensive. Like just go to any page, like, I don't know, CubeSat shop or whatever, and just look at what a simple sensor costs. And it's normally in the region of several thousand euros. It's not like going to a hardware store and buying a small sensor for $2. It's going to cost you several $1,000s to buy a qualified sensor. It's getting more affordable with time. So there are lots of competitors on the market. So in some cases, it's really reasonable to say, you know what, we can buy our CubeSat structure. It's quite affordable nowadays, actually. So it's you can lean more towards the buy with the possibilities that you get on the market. But some parts you may want to make in-house. You want to develop them in-house. It will take a lot of time. You need to design it. But of course, you have a student workforce that doesn't cost the university anything. So it's good to utilize that and to develop new technologies. But then you have to qualify them, of course. So this is something you want to think about for every part of your satellite. And then be aware of different available resources. So what is the general literature that is used, the different handbooks on space technology that are useful. There's a NASA CubeSat 101 that is helpful. What are the CubeSat standards? What are the general standards in space engineering? There's a CubeSat standards handbook about the European space standards. What are the suppliers on the market? So there are very interesting websites like SatSearch or CubeSat Shop, where you can check out the different small satellite suppliers. Software, you want to think about software and ground station networks. What software do you need? Where do you get it from? And what ground station network do you want to use? You don't necessarily need your own ground station. You could use a network. You can ask the amateur radio community to help you out with retrieving your data. But those are things that you need to be aware of. So then let's get started. So we're in an early stage. This is where we define the mission and do a preliminary design. So the main topics here are you define the requirements. So this is one of the main things that we stress in our space engineering study program. Our students, our engineers, have to be able to define proper requirements. So what are the needs? What do you communicate with your engineers that have to build a system actually? So I just met with a student today and explained a little bit more, about half an hour more, about how to actually define the requirements. Thing that is a bit fuzzy in the beginning for beginners, but you will feel that this is a really important part. Otherwise, you may not get the system that you're actually looking for. How do you size the payload? What is it? What type of payload is it? So it depends on that, how you size it. Mission analysis, meaning what orbit do you take? Like, it's probably going to be a low Earth orbit, so in the region of 300 to 1,000 kilometers. And but what specific orbit is it? Is it sun synchronous? Is it equatorial? What launch opportunities do you have that can take you to certain places? What system do you want to take? Like, how complex shall it be? Do you need complicated attitude control, or can you just use a very, very simple approach? For example, like in VISA 3, where you take the Earth magnetic field lines, you use a permanent magnet, and then your satellite roughly aligns with the Earth magnetic field. Of course, it's not super accurate, especially over certain regions, around Earth, but it's feasible for some payloads. So how do you set up the project structure? Like, who are the stakeholders? Then you need to be able to create subsystem budgets. Like, what is the mass budget of your satellite? What is the electrical budget? Like, how much power do you consume? Can you satisfy your needs with the solar cells that you have, and so on. So then what you need in that phase is you need some experts who guide you. So contact universities, or I mean, you have lots of possibilities nowadays with LinkedIn, for example, to contact people who may be willing to spend an hour or two to check, to answer your questions, and the very least for reviews. Like, if you conduct a review, for example, let's say you do a feasibility study, you do lots of calculations, analysis for your mission. Try to invite people with experience for an hour or two who will check your presentation, your document, and will be able to identify the very critical parts and give you comments on that for improvement. Then you need software tools for orbit analysis, budgeting, project management, simulation, computer-aided design. So since you're engineers, you have lots of the tools. I mean, you can use MATLAB for many things. There's some scripts available. There's some free orbit analysis tools that will all be sufficient for those phases. So then the next stage would be detailed design. Now you have a very good idea of what your mission's purpose is, what the budgets are, how the satellite should actually look like. Now the main topics are mechanical design, electrical design, software development. You do lots of simulation, you do prototyping and testing of parts that you newly develop. You think about procurement, and maybe even subcontracting of the development of some parts. So here you can see a model of BSAT-2. So this is actually before integration of a flight model. And you can see the solar cells here. You can see different boards for power control, for onboard computing. You can even see that some are symmetrical, so they're redundant. So this adds a lot of complexity, but also a lot of failure tolerance. You can see the reaction wheel assembly. Those are 3 wheels that are arranged perpendicular to each other. So they rotate, and thus the satellite rotates in the opposite direction. Then you have the top plate here with the antennas that are released with a wire melting mechanism. You have the communication equipment, the GPS transceiver, so this is BZ4. Then you have the camera, the patch antenna, and so on and so forth. And you need to think about the assembly integration. So what you need here are discipline engineers. So meaning from all those different directions. The problem with aerospace engineers is that you have a good idea of different disciplines. You know a little bit of mechanical, electrical, software, engineering. You know the environment, the space environment, if you're a space engineer, and you know all what requirements you need to set up for that mission, and so on. So you know all the aspects well enough, but you don't know enough electrical engineering to develop a circuit board like that. So you're just not an electrical engineer, and you have to accept the fact, and that's okay. So what can you do? What my recommendation is, you're at a university, a big university with several departments. So contact the electrical engineering department, contact your computer scientists, and involve them in the project, involve students from those departments in the project, because you will need them to develop this in the end. Space engineering is very interdisciplinary, so you need people with different expertise, and you as the space engineer normally are kind of in a key function who with connections to all the different engineering branches, kind of a technical project manager. So then you need different software tools to design circuit boards, to do thermal simulations. So a bit more detailed level tools that you may need to either acquire, or you can also use free tools in that domain. And then you need suppliers for several parts. So then let's say you designed the whole satellite, and now you're ready to assemble it and then to test the satellite. So manufacturing, assembly, verification, are things that you think about, but also ground support equipment to carry the satellite, to do tests with the satellite. So here you can see BSAT in a cryogenically cooled thermal vacuum chamber. So the walls are cryogenically cooled down to below -100 degrees centigrade. To kind of simulate the space environment, you see a light source, which kind of simulates the heat from the sun. And then the satellite hangs here, and then everything is pumped out, the air is pumped out, so you have vacuum inside. So that because you don't have convection in space, you only have radiation and conduction. So you kind of simulate the space environment. And if your satellite stays, if your equipment of the satellite stays within the boundary temperature conditions. So the needs here are, you need those integration facilities to integrate the satellite. Luckily, a CubeSat is not too big, so you don't need a super large, very clean environment to integrate your satellite. So you can prepare a relatively small room, and that's fine. So that's okay. But you need testing facilities. For example, if you want to conduct a test like that, where can you do that? Like, where do you get a facility like that? So you can't buy it. Obviously, it's too expensive because you also need to learn how to use it. It's not an option. So you need to outsource this. It's going to cost you. Maybe you can partner up. Maybe your space agency can provide something. So that's what you need to think about. And then you need a ground station. So you need to set up your ground station to communicate with the satellite. So you need a place to do that where you don't have lots of disturbance from the environment. So if you're in a big city, a very crowded city with lots of disturbance in different frequencies, then it may be really difficult to set up a ground station there. So you may have to look for places in other areas. And then once you're ready, your satellite is tested and you feel like you're ready to go and to launch it, then you're in the launch and operations phase. So you need to think about transportation, integration at the launch site. So you can see a colleague integrating BSAT-4 into. Actually, this is interesting. This is another satellite. It's a satellite developed by ROS. It's from the German Aerospace Center, wrapped around this multi-layer insulation, this golden foil, to isolate the satellite from the space environment. And then our satellite, or turbulent satellite, is basically ejected from the belly of that satellite once this one is in space. So it's a different, interesting launch concept, and they perform formation flight in space. So then you need to think about the architecture for operations, like all the software. That's what you need to think about. I mean, sending commands and reading commands and displaying all the commands, just like from the movies, when you see all the different telemetry on the big screens. Where do you get that software from? Of course, you can nowadays there are some more options where you can download or buy similar software, but still you have to modify it. The software that TU Berlin uses was built over the years fully in-house. It's very, very professional, but it takes a lot of time. Then commissioning, calibration. So what do you do once you're in space? You need to think about the different operating scenarios of the first steps. You need to sit down with your team and think about, okay, what equipment do we turn on? What subsystem do we turn on one after another? How do we analyze the data? Do we calibrate sensors, actuators in space? What you need here is professional support. For example, a launch service provider. So there are different companies that offer help in getting a launch spot in one of the launchers, but also helping you with export control, with integration on the launch side, with accommodation on the launch side, etc., etc. They take care of everything, so they can just simply travel to the launch site with your satellite, and many things are handled. So this is something that I recommend. Look at the term launch service provider if you want to launch a satellite. Then mission operations architecture. Yeah, as I said, you need the right software tools. So I'm going to address for a few minutes. I'm going to address some challenges of student-driven space projects. So I walked you through all the different stages and what you need to set up a student project. What are the challenges of specifically student-driven projects? So you need an interdisciplinary team for space engineers, mechanical engineers, electronics, software-related people. involve other faculties, not only aerospace students. So that is a huge recommendation from my side. Use the resources of your university, the brain power. Then you normally have low funding. And that means if you have low funding, that means you don't have experienced researchers who are paid by the government with space experiment, like they have space experience, that they run you through the project. So you probably are almost on your own. So you're a student team with maybe people, researchers, lecturers who want to support you on the side, but you have minimum supervision and also limited resources. So what I highly recommend is try to involve staff members in supervision, and maybe they're even so motivated to help out in more detail. So ask staff members of different departments. Then there's a drain of expertise. So this is a huge problem because a student-built satellite is normally not built within 1 year. You need lots of time. So at least count 3 years from your idea to actually building the first model. And but during that time, students graduate. So they have other priorities, or this is not in part of the coursework, they can't get credits or anything. So every student has their own reasons of they take part in the project, but at some point they leave. So think about how to establish knowledge transfer between seniors and newcomers. This is a very important part. So there should be the right amount of documentation, the right amount of student teaching, and you should offer a way for consultation. So this is definitely one of the difficult problems in university-driven projects. Then you have different skill levels. You normally don't choose the students like you would choose employees. Like when you own a company, you get lots of applications and you choose. When you run a class and you want to do a feasibility study on a satellite, you don't choose the students. You have 20 students, and you have to work with them basically. And they have different skill levels. They have different motivation, different drive. So you need to think about, especially as a lecturer, think about how to establish fair assessment methods and how to promote student leadership. So students can be great leaders in projects. So in my student projects, I always have a team of 2 project managers and 2 systems engineers, and they kind of really drive the progress. They really take on that role of, okay, so I'm going to lead that team. And it's really, really useful. So then, yeah, as I said, low commitment, unpredicted situations. This can happen all the time. So students want to volunteer. So be careful with that as a lecturer, especially, or if you run a student team as a student yourself, you will get lots of questions, lots of other students who want to somehow take part in that project. And if you have the feeling that, hey, this student is busy with other things or can't dedicate as much time, or maybe not so reliable as I need this person to be, then what I recommend is to pay extra attention to critical paths. So there are some critical paths in your project, so with some very important tasks, and use your most reliable, most driven, most skilled people on those paths. And then you have some side jobs, basically, some things that, yeah, they sure need to be done, but they're not so super critical. And you can think about that division of those tasks, and then you can still utilize workforce of people who are maybe not able to commit as much as others. Quality management is important. So you need to establish proper tools for documentation. You need a project management system. You'll have lots of documentation, lots of files over the time, and you don't want to have a mess of where do I find things. So you really need a great tool to where you can find everything in one place. So then keep a consistent workflow. We often have our projects in courses, so students can get credits. but then you have the semester, then you have a lecture-free time, and you have a semester lecture-free time. So that kind of creates an up and down with respect to progress. So you want to make sure that you kind of have a steady progress. You motivate people also to participate in the lecture-free time. So think about that aspect. And then keep in mind the satellite is built by students and not by experienced engineers. So yes, you want to become engineers, you're motivated and probably you're very skilled, but still keep that in mind that this is like a first time experience by people who are not experienced yet. So don't think you will be able to build a satellite as sophisticated as the companies do, and that's totally okay. Many first CubeSats fail, and but from the educational perspective, there's still a very huge success, because the people who participate in the projects, they learn a huge deal in that time. So just going to give you an example of BESA-3. This is Berlin Educational Experimental Satellite number 3. Nowadays, I think we have even number 12 or so is in the pipeline in development. And so it's a relatively simple simple structure. So you can see the monopole antenna for communication. We have one antenna here. Then you have one main board with the bus electronics and the transceiver. The UHF transceiver for communication is separate though. It's a separate board. Then you have on every side you have kind of a solar board, like with solar cells and a sun sensor to detect where the sun is. And then you have at the bottom board you have the S-band antenna because one of the main goals was to verify this S-band transmitter. So this is an S-band transmitter developed by the industry for small satellite space applications, and one of the goals of this project was to test that transmitter on board of the satellite using this S-band antenna. And then you have a battery compartment, and then this hysteresis plate, which is basically for rotation damping of the satellite. And that's it. So it doesn't have the full redundant satellite system like the picture that I showed you before. But this is even still a very difficult endeavor to build a satellite like that, test it, and actually launch it. So here's an overview of the architecture. So we have the electrical power with solar cells, converters, battery, and then charger regulators. The payload here itself is this S-band transceiver with the antenna, and then there's another camera on board. Payload data handling handles the data of that payload. It's basically just a simple microcontroller with data memory on the side. And then you have the onboard data handling, which normally deals with all the different sensor data on board and with controlling the satellite normally. And then you have attitude determination, sun sensors, gyros, communication for telemetry and command. So relatively simple. It's a relatively simple microcontroller that the students used compared to the more complex architectures in the other satellites, and still a very good success to start with that. So if you are able to build a satellite like that, you can take it to the next level. So with the next group, you can improve the architecture, and you can add more failure tolerance. You can add a more sophisticated payload. But first, you need this heritage, you need this knowledge at your department. So, and how we did it is back then, phase 0A, like the feasibility study, started in 2009. We had 21 students in class. And then we went on through the different phases, just like the phases that I mentioned, where you have detailed design, assembly, and we did that in different courses throughout different semesters, total 7 semesters. So we had in total 48 different students who participated in that, and then we had a small student team basically on the side. It is kind of like a core team, and that is something that you need. You need a core team that pushes everything also throughout the whole years here. And then we also had students who wrote their thesis, and that's of course super helpful, because you have a person that works full-time for several months on that project. And then in the end, you have a smaller team of a handful of students who integrate the satellite and then actually make sure that it reaches the final step. Good. So then thank you very much for your attention. I hope this was informative for you, and I'm open to any question.
All right. So thank you very much. And that was amazing, really informative. And I'm sure I can say here on behalf of everyone present that such a guidance, such an approach has never been brought forward in such compressed form. All your years of research and experience compressed into an hour is really going to be helpful for a lot of students.
Thank you very much.
I request everyone to put in your questions in the chat box so that he can answer them very well. And you have this opportunity